Continuing on with section 11.3, looking at the angle between the two vectors, we're looking at this theorem that shows that if two non-zero vectors meet at right angles, if and only if their dot product is 0. So when you're finding the angle between two vectors and you notice that the dot product is equal to 0, you can say that those vectors are orthogonal and the angle between the two vectors is 90 degrees. In addition to finding the angles between two vectors, we also would like to find the angles between the vector and the positive x, y, and z axes. So we can look at finding the angle. Here we have vector v, and it forms an angle with the positive x-axis, or the I vector. Alpha is that angle. Beta would be the angle that the vector makes with the positive y-axis, or the j vector. And gamma would be the angle that the vector makes with the positive z-axis, or the k vector. By applying the formula to find the angle between two vectors, we come up with these formulas here. Cosine of the angle alpha would be v1, the first component of the vector divided by its magnitude. Cosine beta would be v2 divided by the vector's magnitude, and cosine gamma would be v3 divided by the vector's magnitude. Here we have an example where we want to find the direction cosines and angles for the vector v. It has components 2, 3, and 4, and show that cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. By using those formulas, we do want to find the magnitude of the vector v, and we find that it's the square root of 29. So the cosine of alpha is simply the first component 2 divided by the square root of 29. Cosine alpha equals 2 divided by the square root of 29. If you find the inverse cosine of 2 over 29, you'll see that the angle is approximately 68.2 degrees if you're in degree mode. Cosine beta is the second component, 3 divided by its magnitude. And again, using the inverse cosine, you can find that beta is approximately 56.1 degrees. And cosine gamma is the third component, 4 divided by its magnitude. Using the inverse cosine, we find gamma is approximately 42 degrees. Now you can go ahead and make these substitutions for cosine alpha, cosine beta, and cosine gamma, and confirm that this does indeed equal 1. Let's look at this example. Consider there's a boat on an inclined ramp, as shown in this figure. The force due to gravity, which is the green vector pointing straight down, that's force due to gravity, actually pulls the boat down the ramp. That's our W1, as well as against the ramp. That's your W2. W1 and W2 are orthogonal, and they are called the vector components of F. Well, F can be written as the W1 plus the W2 vectors. The forces W1 and W2 help you analyze the effect of gravity on the boat. For example, W1 indicates the force necessary to keep the boat from rolling down the ramp, whereas W2 indicates that the force that the tires must be able to withstand. There is a formula to calculate projections. Let's suppose that we have two vectors, u and v. They're non-zero vectors. We're going to let the vector u be written in components. So again, this is like the force due to gravity can be written as a W1 plus a W2. Two different vectors added together will result in the vector u. W1 is parallel to v and W2 is orthogonal to v. W1 is called the projection of u onto v, or the vector component of u along v, and is denoted by W1, which is equal to the projection of u onto v. Notice the way that it's written. U is bigger and the V is much smaller in subscript, so you're projecting U onto V. W2 is equal to U minus W1, and this is called the vector component of U that is orthogonal to V. This is a formula that's used to determine the projection of U onto V. It involves using the dot product and the magnitude as well as a scalar multiple. What I'd like to show you here is a depiction of this notion of projecting one vector onto another vector. So let's look at what it means to project a U onto a V vector. Graphically, what it means. Let's suppose we have this vector U, and let's say this vector is V. We can project the U vector onto the V vector if you consider a light source that would cast a shadow that would fall perpendicular to V1. For example, if I draw a dotted line, the shadow of the light source would form a 90-degree angle. That's really important here when you're trying to visualize this projection of U onto V. Well, the shadow that the vector makes right here, that is actually the projection of the U vector onto the V vector. That is what we're going to call W1. So this is our W1 vector. That is equal to the projection of the U vector onto the V vector. Now W2 is this orthogonal component of the vector. It's orthogonal to V. We call W2 the vector component of U that is orthogonal to V. And what you can see here, hopefully, is that W1 vector plus W2 vector, you add those two vectors together, this vector plus this vector, the result is equal to the vector U. So that's what graphically it looks like when you're projecting one vector onto another vector. You're looking at that shadow. Let's look at projecting V onto U. That's going to look a little bit different here. Suppose now we want to project, we did U onto V, let's project V onto U. If U looks something like this, the U vector, and V looks something like this, we're going to then cast a shadow onto the U vector. In order to do that, we need to extend this U vector out a little bit. And let's imagine the light source is in this direction. That would cast a shadow that would form a 90-degree angle. That's really important there. Here. So the shadow part is parallel to U. That's going to be our W1 vector. That's the projection of the V vector onto the U vector. The part that's orthogonal to that is going to be our W2. So W1, in this case W1 plus W2 would have to equal the V vector. And again, the order in which you see these written, in this case it's projecting V onto U. All right, here we have an example. We want to find the projection of the U vector onto the V vector and then find the vector component of U that is orthogonal to V. So we want to find the dot product. That would be the part in the numerator, U dot V. 5 times 4 is 20, plus 10 times 3 is 30, over the magnitude of V squared. Well, the magnitude of V would be the square root of 4 squared plus 3 squared. That would be 16 plus 9. That quantity squared, all of that times the V vector. Now the v vector is the vector 4, 3. When you simplify this, you get 20 plus 30 is 50. The square root of 25 squared is 25 times the vector 4, 3. So this ends up being 2 times the vector 4, 3. In other words, 2 v vectors is the projection of the u onto the v vector. So that would give us 8, 6. That would be our W1. W1 is a vector with components 8, 6. Now W1 vector plus the W2 vector, that needs to equal, if you project a v vector. If we already know the W1 vector, we just calculated that to be the vector with components 8, 6, plus the W2 vector, oops, should be a plus sign, plus the W2 vector, that's what we'll be looking for next. That should equal the V vector. Oh, sorry. I'm sorry, that should actually not equal the V vector, it should equal the U vector. So that should be the U vector. And the U vector is 5, 10. Now to get the W2 vector, you can subtract this vector 8, 6 from both sides. So you get that the W2 vector is equal to the vector with components negative 3, 4. So our W1 vector is 8, 6, and our W2 vector is negative 3 and 4. When you add those two vectors together, you should get the U vector. Now the next slide is going to show that depiction. We have our U vector and our V vector. We're projecting the U vector onto the V vector. We'd extend that V vector, it ends up that the projection is twice the V vector. That's our W1. Our W2 is this part right here, which has components negative 3, 4. It's drawn over here, but we remember that vectors can be drawn anywhere as long as they have the same magnitude, same direction. This is our W2. So W1 plus W2 would equal the U vector. The final application for this section on the PowerPoint involves work. If you've studied physics, there's a basic equation for work which is equal to the magnitude of the force times the distance. Force times distance will give you work. Suppose we have F, this vector, that is used to denote force, and PQ indicates the line of motion. Suppose you have a box here that you're dragging along the floor and it's connected to a rope. You're pulling that rope with about 100 pounds of force, and you're moving it from point P to point Q. Well, the work is actually a projection. You can actually project that force vector onto the PQ vector, and however long that magnitude is, so the force, which is the length of the projection, times the distance, that's going to give you the amount of work. Now you can use either of these formulas. You can find the magnitude of the F onto the PQ and then multiply by the magnitude of the PQ vector, which also ends up looking like this, the force vector dot with the PQ vector.